Hello friends, welcome to all of you in our next practical of microwave waveguide test bench. So today we are doing the practical on multi-hole directional coupler. So the objective of this experiment is to measure coupling factor, directivity, insertion loss and isolation loss in a directional coupler. So whatever the equipments we need, it is Klystron power supply, reflex Klystron, isolator, frequency meter, variable attenuator, match termination, then crystal detector, CRO and the basic element that is directional coupler. So dear students, basically directional coupler, it is a 4-port device. So isolator, it is a 2-port device, circulator, it is a 3-port device, but your directional coupler, it is a 4-port device. So port 1, port 2, port 3 and port 4. So 4 ports are there. Now if we apply some input to the port 1, we will get output at port 2, right? So I will repeat once again. If we apply input to the port 1, then we will get output at port 2. Now some amount of power itself gets coupled to the port 3. So if we apply input to the port 1, we are getting output at port 2 and we will get a coupled power at port 3 and no output will be available at port 4. So we can say that port 1 and port 4 are isolated ports. So there is a isolation between port 1 and port 4. So if we apply input to the port 1, we can get output at port 2, coupled output at port 3 and no output at port 4, since your port 4, it is completely isolated from your port 1. So if P1 is the input power, so we can say that the output power measured at second port, it is P2, coupled power, it is P3 and power if we observe at port 4, it is P4, but it is very minimum, right? Or very highly attenuated signal is there, so minimum negligible power we will get at port 4. So for doing the calculations with respect to the power, so coupling can be calculated by 10 log of P3 by P1, isolation itself calculated by 10 log of P4 by P1, directivity 10 log of P4 by P3, insertion loss is equal to 10 log of P2 by P1. Now here you are observing the multi-hole directional coupler in our laboratory. So this is your multi-hole directional coupler. So dear students, it is your port 1. So you are giving input to the port 1, right? Now this multi-hole directional coupler, it is manufactured with the help of two different waveguides. So primary waveguide and one another waveguide which is just placed above the primary waveguide, it is secondary waveguide. So this one is the secondary waveguide, this one is the primary waveguide. So if we apply input to the port 1, we will get output at port 2, right? And some amount of power itself internally coupled at port 3. So at port 3 we will get a coupled power. So I will repeat once again. If we give input to the port 1, output will be available at port 2 and coupled power is available or coupled output is available at port 3. And here you are observing port 4, it is completely terminated with the help of match termination, because no output itself it is observed at port 4, because port 1 and port 4 are completely isolated from each other, right? Now our today's experiment is that we want to calculate the coupling loss, isolation loss, directivity, insertion loss of this multi-hole directional coupler, which is a 4-port device, right? So our basic experimental setup is that first of all we are going to measure the reference voltage. So reference voltage is nothing but the voltage which we are measuring before insertion of a multi-hole directional coupler. So our first reading that we want to take, it is calculate V1. So V1 is nothing but reference voltage, right? So reference voltage before insertion of directional coupler. So V1 is the reference voltage before insertion of directional coupler. So that we are calculating first. So whatever the experimental setup we arranged here, we will just take a review of that. So here you are observing a Klystron power supply. Through this pin itself gets connected to the Klystron, right? With the help of this Klystron mount, the Klystron gets connected to the isolator. Now isolator itself gets connected to the variable attenuator. Now I am keeping this variable attenuator in the extreme outside position for getting zero attenuation. So if we move the variable attenuator in the downward direction, the attenuation increases. So minimum output itself gets observed on the CRO. So basically what I am doing, I am keeping this variable attenuator position to the extreme outside position. So just a minute. So I am rotating this variable attenuator so as to get a maximum upward direction position. So it is zero attenuation position of variable attenuator. Then this is frequency meter. I am rotating it to the one side. Now the frequency meter, it is connected to the slotted line section. Then slotted line section, through the slotted line section, with the help of BNC connector, I am taking output on the CRO, right? So there is detector mount also present, right? Now in our previous experiment, we many times discussed how to generate the square wave on the CRO. Once again I am repeating the same procedure to generate a square wave on the CRO. This is because this is our basic initial procedure for all kind of experiments in waveguide and related with the Klystron, right? So at initial condition, here you are observing a Klystron power supply. So first of all I am keeping the meter select knob on the voltage point. Then whatever the modulation I have selected, it is AM. Now I am keeping beam voltage knob fully anti-clockwise direction and repeller voltage knob fully clockwise direction. Then whatever the amplitude and frequency knob of AM I have kept here at the center position. Then through this pin I have connected the power supply, Klystron power supply, to the Klystron. So just behind your Klystron, we have placed a cooling fan over there, so that whenever during operation, if some excessive heat will be generated within this Klystron, then this excessive heat will be neutralized or cooled down with the help of cooling fan. So this is our basic fundamental experimental setup, basic level setup. Now let us start. Switch on your Klystron power supply. So at initial condition, the beam voltage itself, it is showing 202 volt. So it is needed, it is up to 200 volt, but we are observing here 202 volt. It is also acceptable. Now I am increasing this beam voltage up to 300 volt. So because of this 300 volt beam voltage, your Klystron get respond and the microwave frequencies are generated. So 301 it is also okay. So just after making the voltage, beam voltage 301, we have to wait for 1 or 2 minutes so that your Klystron tube will respond, microwave will be generated, and it will be propagated to the test bench, and finally we are capable to observe some square wave on the CRO. So we will wait for 1 or 2 minutes, right? So meanwhile, whatever the procedure we are following, so first of all we are measuring the reference voltage V1 before insertion of DC. So that procedure we are doing here. Then in the next step, once we observed the V1 as a reference voltage, then we are inserting this directional coupler to this microwave test bench, right? So just after the frequency meter, so I am inserting this multi-hole directional coupler after your frequency meter. So I am giving input to the port 1 of a multi-hole directional coupler. Then I am taking output at port 2 and I will terminate your port 3. So at port 2 the reading we are taking it is V2, which gives us the information about the insertion loss. Then I am just shuffling the output position. So if I am taking in the initial condition at output at port 2, now I am in the next step, what I am doing is that I am just connecting the output to the port 3. At that time your port 2 is terminated. So whatever the output we will get at port 3, it is nothing but your V3, which gives us the information about the coupling factor or the coupling loss. So we have waited for 1 minute. Now I will slowly decrease the voltage, beam voltage, to 265 volt. Okay, 264, 69. Okay, so 68, 7 it is also applicable, acceptable, right? Now the next step is that I am changing the repeller voltage. So before changing the repeller voltage, first of all I will observe the beam current. Now it should not exceed a 30 milliampere. So here you are observing 17 milliampere beam current. So it is acceptable range. Then I am changing the repeller voltage meter select knob to the repeller voltage knob. So at initial condition, whatever the repeller voltage we are observing here, it is minus 275. Now our next step is that to reduce or to change the repeller voltage so that the square wave itself is observed on the CRO screen. So I am changing the repeller voltage and try to generate a square wave on the CRO. Yes, so I have reduced the repeller voltage up to minus 113. Then I have changed the amplitude knob. So as a proper square wave itself it is generated. So dear students, here you are observing a square wave on the CRO. So it is nothing but the output voltage which we are taking as a reference voltage V1 for your directional coupler practical. So if we measure it, so 1, 2, 3, so it is 3.8 multiplied by 0.1. So I will repeat once again, 1, 2, 3, 3.8 multiplied by 0.1 volt. So I will take this reading as a reference reading for a multi-volt directional coupler. So V1 it is reference voltage, so which is equal to 3.8 multiplied by 0.1 volt. so which is equal to 38.38 volt. So V1 is your 0.38 volt. Now if we change the slotted line section in forward or reverse direction, we observe that the maxima and minima points. So this is the point, or this is the optimum level of output voltage we have observed. So 3.8 multiplied by 0.1 volt, that is 0.38 volt. We are taking this V1 as a reference voltage, that is before insertion of your directional coupler. Now our next step is that now we are inserting this multi-hole directional coupler in our experimental setup just after the frequency meter. So I am giving input to your port number 1, we are taking output at port number 2, and we are terminating port 3. So our next step is that insert directional coupler. So port 1, it is input port, port 2, it is output port, and port 3 terminated. Port 4 also, it is inbuilt terminated, because this device is manufactured in such a way that port 4 it is always terminated with the help of match termination. So input port it is port 1, output port it is port 2, then 3 and 4 it is terminated. So input it is port 1, output port it is port 2, port 3 we are terminating, port 4 it is already inbuilt terminated, right? So wait for a meanwhile, I will just connect a multi-hole directional coupler and then we will take the readings. Yes, so dear students, here you are observing that I have inserted a directional coupler in the microwave waveguide test bench setup. So I have done the same procedure for generation of a square wave which we have adopted at the initial condition for calculation of V1. The same step I have once again repeated for generating the square wave on the CRO after insertion of a directional coupler. So here you are observing a Klystron power supply through the connector. It is given to the Klystron tube. Microwave itself it is generated. Now here you are observing that I have given input to the port 1 of a directional coupler. I have taken output at port 2 of a directional coupler, and I have terminated this port 3, right? So input given to the port 1, output observed at port 2, port 3, and the port 4 itself is terminated with the help of match termination. So here we are observing the output voltage. So it is approximately 3.8, right, into 0.1. So it is exactly equal to your reference voltage. So now insert DC. So we have inserted, given input to port 1, output at port 2. So V2 is nothing but output at port 2, right? And its value it is 3.8 multiplied by 0.1 volt. So it becomes 0.38 volt. So it is nothing but the V2. So with the help of V2 we are capable of calculating the insertion loss. So formula for calculating insertion loss is insertion loss is equal to 20 log of V2 by V1 in dB. So we know the value of V1, we know the value of V2. So just keep here V2 value, V1 value, and calculate your insertion loss, right? So we have given input to the port 1, we have observed at port 2, right, and your port 3 it is terminated. Now the next step I am doing, I am just changing this port. Now I am taking output at port 3 and I am terminating your port 2. So taking output at port 3, terminate your port 2. So it will give us the coupling factor. So we will wait for a meanwhile. I will just do the connection. Yes. So dear students, I have connected the directional coupler. Now I have terminated the port 2 and we are taking output at port 3. So input it is given to your port 1, port 4 is also terminated. Now I have terminated port 2 and we are taking output at port number 3. So you are observing a square wave over here. So we will take the reading as a V3. So 1, 2, 3. So 3 multiplied by 20 millivolt, right? So it is nothing but your V3. So in the next step, port 1 it is act as the input port. Now port 2 it is terminated. So in our previous experimental procedure we have taken output at port 2. Now we are terminating port 2. At port 3 we are taking output. So in previous step port 3 itself it is terminated, and at port 4 match termination is present. So port 2 and port 4 are terminated. We are giving input to the port 1, taking output at port 3. So whatever the reading, it is V3. So once again we will take the reading. So 1, 2, 3 multiplied by multiplication factor 20 millivolt. So 3 multiplied by 20 millivolt. So it is 60 millivolt. So 60 into 10 raised to minus 3 volt. So it is nothing but your V3, sorry. So now as we already discussed that it is the coupled power. So it is minimum value, having minimum value to that of your direct power. So V3 is very much less than that of your V2, because whatever the power we have measured, it is the coupled power. So with the help of this reading we can calculate coupling factor. So coupling factor it is equal to 20 log of V3 by V1 in dB. So V1 is the reference voltage what we have measured before insertion of directional coupler. Now V3 it is nothing but the output voltage measured at port 3, so which is a coupled power. So the coupling factor it is 20 log of V3 by V1. So we know the value of V3, we know the value of V1, then we can easily calculate your coupling factor. Now our next aim is to calculate the isolation loss or the isolation between the neighborhood ports, right? So if we say that if port 1 and port 4 are the neighborhood ports, right? So they are also known as the isolated ports, right? So if we give input port 1, no output itself it is observed at port 4. But if we want to take or if we want to take the output on the CRO, it is permanently terminated. So we can't connect a CRO connection to your port 4. So in the next procedure, what we are doing, we are just giving input to your port number 2 and we are taking output at port number 3. So if port 1 and port 4 are isolated ports, in the similar manner port 2 and port 3 are also the isolated ports. So that's why we are giving input to the port 2. If we give input to the port 2, at that time your port 3, it is also isolated. So we are just changing the direction of a directional coupler, and now we have given input to the port 1. In our next procedure, we are going to give the input to your port number 2 and we are taking output at port number 3. So wait for a meanwhile. So dear students, now I have connected input to your port number 2 and we are taking output at port number 3. Now here port number 1 it is terminated, port 4 it is also terminated. So these two ports are terminated and we have given input to port number 2 taking output at port number 3. So our theory says that if we give input to the this port, there is no output at this particular port. So these two ports are isolated ports. So here, though I am changing the repeller voltage, here you are observing there is no any change in the output voltage. So no any square wave itself it is generating on the CRO. So though I am changing some knobs of your CRO, making some adjustment, then though I am changing here the repeller voltage, right? So from minus 275 76, I am also reducing the repeller voltage, but no any kind of output itself it is observed. So this is nothing but a isolation. So no output itself it is observed, right? Okay, so if we take this reading as V4, so for calculation of your V4, your port 2 act as a input port, port 3 act as a output port, port 1 and port 2, both these ports are terminated, right? So V4 is 0 volt, so no output itself it is observed, or minimum it is possibility to observe the minimum output, but here we are not getting any output, so V4 is 0. So we can say that isolation is equal to 20 log of V4 by V1 in dB, right? So we know the value of V4, we know the value of V1, then we can easily calculate isolation. One another parameter of directivity also we have to calculate. So directivity is equal to 20 log of V4 by V3 in dB. So we know the value of V4, we know the value of V3, we can easily calculate the directivity. So just by calculating the value of V1 as a reference before insertion of directional coupler, then finding out the value of V2 at the output gives us the insertion loss V2 by V1, 20 log of V2 by V1 in dB. Then we have taken output at port 3. So by calculating V3, we can get a coupling loss or coupling factor 20 log of V3 by V1. Then just by rotating or reversing the ports and giving input to the port 2 and observing output at port 3, we can get next reading, that is called as V4, which gives us the value of isolation, and finally directivity itself, it is calculated by 20 log of V4 by V3. So this is all about the experiment of multi-hole directional coupler. So thank you very much.